Chapter 3, The Chemistry of Climate Change, Part 4, and the final lecture for Chapter 3. In this lecture, we're going to cover a term called the global warming potential, which places gases on a relative scale with carbon dioxide as the standard or baseline. How we evaluate the impacts of global warming, looking at different scientific models which try to predict the possibilities for how warm will actually become. We'll look more in depth at the consequences depending on how much warming occurs of climate change. And what can we do about climate change on a daily basis? Global warming potential is a numerical value that takes a certain mass of carbon dioxide and says, okay, the amount of heat trapped by that carbon dioxide is 1. We'll call that the numerical value 1. Say 10 grams of carbon dioxide absorbs this much heat. That heat we'll call 1. Now, if we had 10 grams of methane, relative to that amount of heat carbon dioxide traps, methane for that same amount of mass traps 10 times more heat. And that value of 10 is a nice simple go-to number which tells us very readily that, okay, if you have the same amount of methane as carbon dioxide, we're going to be 10 times warmer. And whether or not a gas has greater or less global warming potential than carbon dioxide is based on how long it remains in the atmosphere. Does it break down quickly, or does it stick around and radiate heat back to the Earth for a significant amount of time? Also, does it absorb a lot of IR radiation? Does it have just a very tiny wavelength of IR radiation that it absorbs and re-emits? Or does it absorb a wide range of infrared radiation wavelengths and starts bending and vibrating and scissoring and doing all this weird things for many different wavelengths of IR radiation? So let's take a look at a video on global warming potential. So again, just to summarize, global warming potential is a relative scale. So here you could see carbon dioxide. It has some concentrations listed. It's rough atmospheric lifetime. And it's given a global warming potential of 1. And again, methane, its relative concentrations, its atmospheric lifetime. And we're basically saying for the same mass of methane, if you had the same concentration of methane as carbon dioxide, it would have 21 times the warming potential. But you can see there's much lower concentrations of methane. So even though methane can trap much more heat than carbon dioxide, the concentrations are so much lower, they're not as big of an influence as carbon dioxide. And for that reason, that's why we focus on carbon dioxide mainly as a greenhouse gas, just because we're spewing it out of the tailpipes of our cars and coal factories at such an incredible amount. Nitrous oxide, again, parts per billion. CFCs, chlorofluorocarbons, parts per billion. Yes, their global warming potential is much, much higher. They trap per gram of gas a much larger amount of heat. But we're not producing them quite as significantly as carbon dioxide. But this tells you something about, okay, if we evaluate the global warming potential for a certain gas, we need to be very careful about how much of it we produce and how much of it is emitted into the atmosphere, so it doesn't become a significant contributor. Thinker Buddy question. Considering the following information about 2 greenhouse gases. The gas dinitrogen monoxide has a greenhouse factor of 160 and an abundance in the troposphere of 3.0 times 10 to the minus 5%. CCl2F2 has a greenhouse factor of 25,000 and an abundance in the troposphere of 4.8 times 10 to the minus 8%. CCl2F2 is a blank effective greenhouse gas and dinitrogen monoxide, and there's blank of it in the troposphere. And I believe that's Freon 1. Is Freon 1 a more effective greenhouse gas and there's less of it in the troposphere? Or B, is it a less effective greenhouse gas and there's less of it in the troposphere? Or C, it's a more effective greenhouse gas and there's more of it in the troposphere? Or D, it's a less effective greenhouse gas and there's more of it in the troposphere? So we're looking at that global warming potential factor. And Freon 1 has a global warming potential factor of 25,000. That's much larger than the 160 for N2O. So it is a more effective greenhouse gas. But there's much less of it in the atmosphere. This 10 to the minus 8 is a smaller number than the 10 to the minus 5% abundance of N2O. So we have to look at a number of different things to determine what influence a gas has on global warming. Thinker Buddy question. Which factors should be considered when deciding which greenhouse gases should be targeted for control? Roman numeral 1, absorption of IR radiation. Roman numeral 2, the relative abundance. Roman numeral 3, atmospheric lifetime. All three of them need to be considered. To what degree a molecule absorbs IR radiation and re-emits it, the abundance of that gas, is it becoming a significant percentage of our atmosphere, and how long does it last in the atmosphere? When trying to determine how warm we will get, we need to look at all the factors which absorb heat and keep heat in the earth, and those factors which reflect heat and remove heat from the earth. The term we use to describe whether or not heat is kept in or ejected is called radiative forcing. So some of the factors involved in radiative forcing is solar irradiance. So when there's fluctuations in solar intensity, we are going to receive more radiant energy. So there'll be a net increase in energy in the earth. Greenhouse gases, we've talked about those. They're the largest anthropogenic factor in keeping heat in the earth, and the gas is re-emitting this heat energy back to the earth instead of allowing it to escape. Land use is also a big radiative forcing factor. How much are we reflecting light back to the atmosphere and beyond? And glaciers actually reflect a significant amount of energy back out into the solar system. When they melt, this amount of energy reflection decreases. And the fraction of radiation that is actually reflected is called albedo, or surface albedo. Aerosols are also a factor in radiative forcing, and they include a very wide range of systems: dust storms, ocean spray, forest fires, volcanic eruptions, basically anything that kicks up fine particles into our atmosphere. So let's take a look at a video exploring the concept of radiative forcing. So to summarize again, radiative forcings are factors that affect the balance of heat in the Earth. We've looked at greenhouse gases, carbon dioxide. They increase the heat trapped in the Earth. Now this radiative forcing, just if you look down here, is measured in watts per square meter. You don't have to worry about that, but I just wanted to let you know watts is a measurement of heat, and they're doing it over a square meter. We talked about methane as a greenhouse gas, nitrogen dioxide, CFCs. They all are greenhouse gases and increase the heat trapped in the Earth. Ozone reflects heat, or essentially when light hits the ozone, it breaks apart instead of hitting the Earth. So stratospheric ozone actually reduces some of the heat versus tropospheric ozone. When it's at the surface of the Earth, it tends to trap in heat. We talked about the surface albedo. If you have something like a glacier, it'll reflect heat. If you have asphalt or black carbon on snow, polluted snow, it absorbs heat and keeps that heat in. Then there's aerosol effects. There's different aerosol effects, and they essentially, all aerosols reflect heat. And that was actually, remember, if you go back to part 1 of chapter 3 lecture, the first slides I showed involved trying to offset global warming by essentially spraying aerosols into the sky using ocean water. And then there are natural causes of radiative forcings as well. Fluctuations in solar irradiance will increase the amount of heat trapped. Thinker buddy question. Blank radiative forcing contributes to cooling the Earth while blank only causes warming. A. Surface albedo and carbon dioxide emissions. B. Methane emissions contribute to cooling while ozone only causes warming. C. Aerosol contributes to cooling while methane only causes warming. And D. Surface albedo contributes to cooling while irradiance, solar irradiance, only causes warming. The answer is C. Aerosols contribute to cooling. They reflect all of the sun's heat, or at least the heat that strikes the aerosols and reflects it, while methane is a greenhouse gas. It doesn't cause any cooling. It absorbs energy and reflects it or redirects it back to the Earth. Now, there are climate models that essentially agree with what we're observing in terms of temperature changes. If we look at natural forces, the natural contributions to heat trapping on Earth, we would not see the temperature increases that we see. So some models predict very well, taking into account human effects or anthropogenic sources, that yes, it's likely those anthropogenic sources are causing warming. And we can use models as well to predict future temperatures. So here, this black line here is data for the 20th century, and now these other lines are predicted temperatures. And models are scientific constructs. They're created and scientists make certain assumptions when they create these models. They say, okay, for example, China is going to continue to grow by 5% every year, and their energy consumption is going to continue to grow by 10% a year for the next 20 years. Based on that assumption, they can then calculate looking at the amounts of greenhouse gases that are produced, they can maybe predict a temperature increase. But again, that assumption has to be made. Perhaps after 5 years, China, their growth slows. They turn to nuclear energy using thorium or alternative energy. It's very difficult to predict the future. That's what many people use as an argument against taking action against global warming. And to be honest, my opinion is I agree with them. It is very difficult to determine the consequences of global warming, or at least some of them. However, again, what's the worst that can happen? The worst that can happen if we don't take action is that the most dire scientific models are true. And we'll talk about some of the consequences of that in a moment. And the best case scenario is that we create a healthy, more sustainable Earth. And of course, we want to do it keeping in mind the triple bottom line. We don't want to make undue sacrifices to social systems, environmental systems, or industrial systems. We want to just think about what we're doing in order to do it more effectively for not only us as a people, but also for the environment and to maximize profits. And so far, we just have not even done that to a significant degree. We've only been focusing, at least industrially, on profit. So just a slight shift in how we approach our day-to-day life. Not only could it improve profits for business, but it could improve both social and environmental health. Scientific models are A, based in past observed trends and data to predict future possibilities. B, varied in their predictions. Scientists tend to disagree on the extent of the consequences of global warming. C, are often based in mathematics, but generally computers and math are used for complex models. D, not used only for climate change. Many scientific phenomena can be modeled. E, all of the above are true. E is correct. Scientists generally look at past data and try to create a model to explain how that data occurred. Once they've developed something that agrees with past observations, they try to use it to make predictions about the future. Models are different. The factors that scientists emphasize to explain past observations may be different. Many different models may work for past observations. However, whether or not they agree with future predictions can be variable. And that's why there's a fair amount of disagreement as to how much global warming will occur and what the impacts will be. C is also true. Models often use mathematics, and certain equations are typically developed to make predictions, and often computers are used. And scientific models are used all over the place, not just for climate change. Many scientific phenomena can be modeled. Let's take a look at a video exploring the future of global warming. In 2007, an intergovernmental panel on climate change met. There were 2,500 plus scientific experts, 800 plus contributing authors, 130 countries, all to put together one report assessing climate change. And all of these countries agreed that it was very likely human-caused emissions are the main factor in what we see in temperature changes since 1950. We're seeing higher maximum temperatures. Precipitation has increased. These are very likely conclusions from the data. Also, likely conclusions is that our ice thickness in the Arctic has decreased significantly. Temperatures in the northern hemisphere has been the highest of any century in the past 1,000 years. Increased rainfall, summer droughts have increased. What's very unlikely, based on this intergovernmental panel on climate change, is that the warming is due to climate variability alone, just natural variability. It's very unlikely. One impact of global warming is continued sea ice disappearance. Since 1979 to 2003, we've seen a significant amount of ice disappearing from the Arctic as well as over Greenland. So the more we warm, the more that ice is going to disappear and change those ecosystems. Acidification of the ocean is actually an impact due to the concentration of carbon dioxide alone. As carbon dioxide increases, it dissolves in the ocean and forms an acid, thereby changing the essential biological nature of the ocean. Animals and coral and other species are very sensitive to changes in acidity. And we're going to talk about acids and bases in a later chapter. Extreme weather is another prediction as far as the impact of global warming. People feel as if we've seen that already with Hurricane Sandy in New York, and they're actually assuming in New York, without significant changes to our destructive ways with regards to producing global warming gases, that they're going to have other Hurricane Sandys, and they're trying to modify their infrastructure accordingly. And of course, these events are hitting taxpayers in the pocketbook. Even if you don't believe them, if we continue, or even if you don't believe in global warming, if we continue to see larger numbers of extreme weather events and they cost us more and more money, it doesn't really matter the cause. Something is happening. Now, to be honest, this data here, if it's looking at strictly the cost of extreme weather events, yes, it looks like since 1980 there hasn't been all that much change. And in the 2000s, we did see some spikes. Um, to me, this particular slide isn't the nail in the coffin. It's just trying to illustrate more, okay, global warming and these extreme weather events are going to really have an effect on every country, not just coastal areas. Biodiversity will also be a huge factor if we do warm significantly. Animals can only migrate so far. They can only adapt through so many generations to large changes in temperature. If we have sudden, rapid increases in temperature, changes in weather patterns in certain areas, we're going to have significant impacts to our biodiversity on the planet. So this slide shows nicely the summary of global warming impacts. We've got extreme weather, ocean acidification, which effects could take many years to undo. This says several thousand. Again, that's using which scientific model, we don't know. That's very hard to quantify. Ecological, species extinction, social. Yeah, it might actually have a mix of positive and negative impacts, but unfortunately, the most negative impacts will be in developing countries. Might have a positive impact in colder regions in the northern hemisphere. All of a sudden, they might become a lot more habitable. But in warmer areas in the around the equator, it just might be completely inhospitable. And then large-scale impacts can, if there are large portions of the Antarctic ice sheets and the ice sheets around Greenland that suddenly melt or descend into the ocean, we could see very rapid rise in sea level. Thinker buddy. Possible consequences of continued global warming include A. Lowered sea levels, leaving present coastal areas far inland. B. Altered climates and changes in agricultural productivity. C. Increased deforestation in areas such as the American Midwest and South American rainforests. D. Further destruction of the ozone layer, leading to increased skin cancer. Or E. All of the above. B is actually the best answer. A is not true. We're talking about rising in sea levels. Um, we are looking at altered climates, and therefore, if we change perhaps the amount of sun in California, which is really a significant producer of food for the country, if it becomes much warmer, its productivity will decrease. So it's going to change the agricultural productivity, the amount and the types of plants that can be grown there. Deforestation, you could argue that severe changes in temperatures for certain regions may affect plant life. However, deforestation, that term more frequently refers to anthropogenic deforestation, meaning we are cutting down large swaths of forest. The ozone layer, that's more due to what we talked about in chapter 2 as far as chemicals we're ejecting into the atmosphere that act as catalysts to break down ozone more so than uh, the natural destructive cycle and regeneration of ozone. So, what can we do? Are we just totally at a loss? One idea is that power plants that release CO2, such as coal plants, pump that CO2 into depleted oil or gas reservoirs or deep into the ground, and that carbon dioxide essentially interacts or reacts with minerals in the earth, and instead of bubbling to the surface, it forms solids like calcium carbonate. It's one idea. It's been pursued to some degree, but it hasn't shown economical effectiveness yet. Another idea that's being used more effectively in Europe than I believe in the United States at this point in 2013 is called a cap and trade system. It's where a company is allowed a release of so much carbon dioxide. If they go beyond that cap, as far as a limit in carbon dioxide release amounts, then what they can do is they can purchase or trade with other companies or other entities which perhaps aren't using all of their CO2 allowance. So here we see this company here on the left. They have only released a little bit of CO2, but they were allowed much more. And this company on the right, they are just releasing CO2 like crazy, going over their cap. And what they can do is buy unused CO2 allowances from the company on the left. Reforestation. There are a number of organizations working to pay local populations to reforest areas that have been previously deforested. The more trees we can plant, the more they will absorb CO2. However, at this point, the number of acres we lose daily is much greater than the amount we are able to replant. Of course, if we put more resources and efforts into replanting and try and work with countries to find sustainable methods of generating income versus cutting down their forests, we may actually have an impact one day. This graph here is from this author Paciella and Soklo, 2004. Using a particular model, they predict that the billions of tons of carbon in 2050 will reach this point if we don't make any changes to how we generate energy and how we transport commercial goods, etc., etc. And of course, the goal is to, instead of continue to increase the amount of carbon dioxide, to actually decrease it. So how do we do that? Well, we need to look at different ways of producing electricity, maybe using electricity more efficiently. We need to improve the efficiency of our vehicles, perhaps biofuels, use carbon dioxide capture and storage. I would add maybe uh, thorium nuclear energy as well to move away from fossil fuels, and we'll talk about that in Chapter 7. Can you make a difference? Well, every little thing counts. Definitely contacting your legislators when bills come up that may influence the amount of greenhouse gases released, or perhaps anything that affects our forests and anything that would capture carbon dioxide. Um, just reducing your energy use. A lot of our energy is still generated by fossil fuels, which release greenhouse gases. Heating of water also takes energy. Not just heating of water, but actually generating the water also takes energy. Even if you're taking long cold showers, of course it's better than hot showers, but it still takes energy to get that water into your home and clean it. Simple things like keeping rooms cool by closing blinds or shades instead of just running the air conditioner, turning off lights, using LED light bulbs. Fluorescent light bulbs have been popular lately as a way to reduce energy use, but unfortunately they contain a certain amount of mercury. They actually aren't very ideal. Coming on the market very soon, well, they're on the market now, these LED light bulbs. They use a significantly less amount of energy than fluorescent, and they are much safer, non-toxic. Right now, they're fairly expensive though. Perhaps a fluorescent light bulb might cost you $4. The LED equivalent could cost you $30. So much more expensive. They do last much longer, but there's that initial expenditure. Hopefully they'll come down in price in the future. So keep your eye open for a relatively affordable LED light bulb in the future. This ends the last part of Chapter 3.